You have
Yeah.
the summary.
By the way, you could send us the slideshow as well later, and
Okay.
we will put it in our Dropbox.
Right. So I was, please confirm that you see this slide where you see the defects.
Yes.
Okay, very good. So this is just an entry to tell you that these defects have been realized pretty recently from the 90s, and this is the Gross-Pitayeski equation. A nonlinear cubic term is here, and this equation is a mean field equation for the condensate, and this was introduced in 1961, basically by these two people, Gross and Pitayeski. Pitayeski, by the way, passed away in August, last August in Trento. He was in Italy for many, many years. So you see here the boundary condition. We assume that condensate is everywhere, and as we go to infinity, this mod psi, the wave function, goes to 1, and the wave function psi is function of the vector position x and time t. Now, in the 20s, 1927, Madelung introduced this transform by coupling the so-called fluid density, although is a gas of bosons. Anyway, this fluid density rho with theta, and theta is the phase of the wave function. If we take grad theta, we can create a vector, and we can show that this vector plays the role of a velocity field u of a virtual fluid. Now, by using Madelung transform, amazingly, we can reduce this mean field equation to this couple of equations by taking imaginary and real part. And the one part gives us the continuity equation, which is exactly the classical continuity equation we have in fluid mechanics. And the other equation, which is this one, is a linear momentum equation. As you can see, we have the acceleration du dt, material derivative of the velocity in time, given by these two terms. Now, amazingly, this equation resembles very closely the Navier-Stokes equation because formally is represented by the same equation. There is a big difference, however. There is no pressure here. The pressure is represented by density squared over 4, and what plays the role of viscosity terms in Navier-Stokes here is given by this gradient of the various gradients of the density. So it's a purely function of velocity and density. Of course, there is no pressure. Because of this, we can take advantage of the great progress that was done in simulation, direct numerical simulations of fluid flows and visualization, of course, of these simulations. Now, I want to just justify the fact that why we care about quantum knots. Well, quantum knots have been found since people started to have a close-up view of turbulence, of quantum turbulence. This is a picture from direct numerical simulations of vortex tangles. Then more recently, we have vortex knots in optics, in geometric optics, and also the evidence that indeed these defects can form highly complex knots in superfluid turbulence. So this is just basic information about relevance of knots in quantum systems. Let me remind you the key concepts that will play a role in this. One is helicity. Helicity is just given by the integral of the velocity field times vorticity on the volume of vorticity. And we assume that the volume of vorticity, in our case, highly localized vorticity in thin tubes, the boundary of these tubes is a vortex surface. Plus, we assume, for simplicity, divergence-less condition for U. That is not strictly necessary, but is just a simplification in our approach. Now, kinetic helicity, this is the classical definition, has been proven to be conserved by Moreau, 1961. And similarly, magnetic helicity, if we replace U and omega with the vector potential of the magnetic field and the magnetic field. Now, under GPE, we have a very interesting situation. Under GPE, we can prove, a rigorous proof was only given very recently by Andrea Belloni and myself, but already there is a significant information on this by Salmon in 2017, where we can see that helicity in the case of Gross-Pitayevsky equation is actually zero all the time. And this is because we deal with localized fields, and defects are indeed singular in the sense of being nodal lines for the wave function. So are actually geometric curves where vorticity is just a Dirac delta distribution, and using distributional techniques, we could prove with Andrea this result. So we start from the fact that helicity is zero, and we'll see what happens. Now, an interesting connection with topology comes from the work of Keith Moffat, 1969, and we can say that if we deal with the link of the disjoint union of defects in an ideal fluid, let's say, then helicity, the classical form given by this integral, can be represented by this sum. And this sum takes care of the Gauss linking number, LKIJ, and the self-linking number, the way I will define it later, given by this SLI. The gammas are the circulations of the vortices. Now, in case of GPE, we have that the helicity, the classical helicity, is always zero. It means that this summation is zero all the times. But also gammas are basically, in the context of condensates, all equal to 1. So we can even simplify further this equation to this form, where I just represented the self-linking number given by the sum of these two contributions, the writhe and the twist of each component. Now, let me clarify what I mean by that. Well, we all know very well a Gauss linking number. So the Gauss linking number is just one of the fundamental topological invariants of links, which is given here in the standard way as Gauss did it in 1833. And then we have this additional contribution, the self-linking number of each component. Now, this was derived by Calogerianu and then eventually extended to higher dimensions by White, and we make use of a mathematical ribbon. My way to just summarize what we have in mind to do is this, is a very, very rough, say, introduction to this definition of mathematical ribbon. Now, imagine that we did with one component of this link, and then we construct the second component, say L2, let me call it Li star, based on the first component. And on the first component, we add a vector field, a unit vector field that we may call a frame to the first component. At this stage, the two curves are still separated by an epsilon apart, and then we can see that the linking number of these two curves is still well defined. But when we take the limit as epsilon goes to 0 of this linking number, then we get this quantity. And this quantity was proven to be a topologically invariant quantity by Calogerianu. Of course, this quantity became very famous through the work of White and others in biology because it can be written in terms of the sum of writhe and twist. twist of the mathematical ribbon and right of, say, the center line, if we like, of this defect, if we refer to defects. This is the formula of right, as you can see, resembles closely the Gauss linking number and takes care of the coils of our defects in space. Total twist, dW of Ri, can be written in this classical fashion, this way, but as we did with Keith, it can be proven to be sum of two parts, total torsion and intrinsic writhe, an intrinsic twist. Now, this is just a schematic representation in case torsion is highly localized here, or in the other case where torsion of the central line is 0, and we have this intrinsic twist. Of course, I refer to closed curves and closed ribbons all the time. Now, Zephyr surfaces are also a very interesting tools for research. We all know this, given a knot L, a Zephyr surface for L is an orientable surface with one boundary component, such that the boundary component of the surface is the knot. Now, it's important to remark that our surface has to be orientable, not only because we refer to a Zephyr surface, but because of the physics. Okay, the Zephyr surface for the link, of course, is given by this case where the link is indeed the boundary. Here we have a picture from Van Wyck on Zephyr view. Since a defect is a nodal line of psi, we can identify the defect with a knot or a link, and each isophase surface of the psi function, of the wave function, can be identified with a Zephyr surface. So instead of having this, we can think of a Zephyr surface in green as a special case of one of the many Zephyr surfaces we can pick, or one of the many, infinitely many isophase surfaces we can pick. Since a nodal line is the result of the intersection of infinitely many isophase surfaces, each being a Zephyr surface for L, then the entire space results foliated by Zephyr surfaces for L. If we have only one L, then this is a different story. It's also interesting. Here you have a picture. Suppose that the blue, blue part here is a defect. Vorticity is along this defect line. Then we have these space foliated by this book decomposition. If the defect forms a ring like this one, a vortex ring, then of course these surfaces form several spherical caps, as I shown there. Remember, infinitely many. It's like soap films, if you like, to think of soap film. At least this was my line of thinking when we approached this problem with Zephyr surfaces. Now, evolution of Hopf-Link has been done by several authors. Here I show you very, very briefly what was done by Simone Zucker and myself already 6 years ago. We start with the link. There is a reconnection here, so there is a change of topology here, and then a further reconnection here, so a secondary reconnection and the formation of a smaller loop, and then a third reconnection with the formation of 3 distinct loops. Of course, imagine that these loops are displacing themselves in space and going away one another according to their mutual inductions. Now, a framing. This is a bit of a problem for defects because indeed we deal with curves, essentially, where vorticity is, as I said, delta Dirac function on that. And so we need to take care of this framing. We use a Zephyr framing to be short. Framing for L is a Zephyr framing if we consider the push-offs contained on this surface, on the Zephyr surface. Well, this is a piece of a result that research that was done with Imra Cruz-Wright and Dewitt-Sumners, where we showed that simply if our link has a Zephyr framing, then evidently total helicity, or the sum of single helicities, sum up to 0. This is consistent, of course, with what I told you at the beginning about proving by distributional techniques that helicity under GPE is exactly 0. So the framing is a cipher framing if and only if this condition is satisfied, which itself is a very interesting condition because it constrains linking numbers to obey this 0 sum. A lemma cipher framing is conserved by anti-parallel reconnection. As a result, the cipher framed curves under reconnection, under anti-parallel reconnection, writhe helicity and twist helicity are both conserved. As a corollary, because helicity, or if you like, total linkage is conserved, the corollary of this would be that also intrinsic twist is conserved. That means that under reconnection, we reconnect also cipher surfaces into new cipher surfaces that keep the orientation, the original orientation. This is the extra bonus we have from this result. Okay, as a proof, numerical proof that was done already in 2017, that indeed total helicity remains 0 throughout the evolution. You see these dots here, and they are just marking the time where we have reconnection and the link change into 2 loops and then eventually 3 loops. Here is just a way to show you the balance between writhe and total twist. Of course, I want to spend time on telling you all the details about how to say just incidental situation on this evolution, but you see here what happens about this evaluation of different writhe and twist. So the decay of a component like a Hopf-link into separate loops has been investigated by many other authors, and the common view of this phenomenon is the following. Well, you start with say, much more complex configuration. For example, the 2-5 torus knot that you have it there, and then you expect, if you assume for simplicity that there is only one single reconnection occurring at anti-parallel reconnection occurring on your defect, then you expect to get, for example, the 2-4, and then the 2-3, and then the 2-2, and then the unknot, and eventually the formation of separate loops. This is the typical cascade that has been seen and also produced in the lab by the group of William Irvine, in particular, starting from the trefoil knot down to the separated loops, but that has been also observed in analysis of the topoisomerases on DNA. I want to add something to this because this is the common belief. What about, is any chance to go back in this direct topological cascade? And anyhow, why is so difficult to produce a trefoil knot starting from unlinked circle? That was actually the dream of Kelvin. Kelvin asked Tate to shoot several vortex rings and to produce a trefoil knot, failing to do that. And the reason why they failed is very simple. I have a movie to show here. I'm a little bit afraid to waste my time. I'll try first to tell you a few things, and then if I am successful, you'll see the movies. So the first thing is that not necessarily we might have actually is very rare to have one reconnection at a time. It is also pretty rare to have instantaneous reconnections at all possible places. And here we are in the other limit. We take the 2-9 torus knot, which is here, and we let it evolve. I have a movie for that. And when we let it evolve, because of the highly symmetric configuration that we imposed in the computation, then you expect that then a number of reconnection occur instantly at all places, and indeed they do occur, with the instantaneous collapse of the topology from the trefoil knot to two loops, and then further, due to the highly bent region, again an instantaneous reconnection to form these smaller loops. So this is the other extreme. We do not follow the cascade as I showed you here through one single reconnection at a time, but the instantaneous reconnections. The second movie I'd like to show you, let me go first to the completion of this slide, is the Kelvin's problem that allow me to say that has not been realized so far till we did the simulation. Of course, I mentioned the production of a trefoil knot of the group of William Irvine in Chicago, but remember the topology of the trefoil knot in that case was somehow inherited from the topology of the trefoil shaped area. We have the slide here first, and then I'll try to show you the movie. So the slide shows you the key instances where we can start with the two separated loops, unlinked, unknotted. You can well see this in the projection plane, or just infer what I'm saying from the slide. And then as time progresses, there is a first reconnection where there is one long loop formed that is evidenced by the color, and then a secondary reconnection occurring where a Hopf link is formed, and then a third reconnection where a trefoil knot is formed. Now let me go back to the slide, and you see we start from a situation where we have two disjoint unknotted, unlinked loops, and then a formation of a single loop, then the Hopf link, and then the trefoil knot. So we could prove the dream of Kelvin, that indeed this is realizable. Why is so difficult to do this? Well, very simple, because you need to specify an extremely careful initial condition given by this t equals 0 situation. By this, I mean the geometry, the local geometry, has been engineered so that you can, through natural evolution controlled by Gross-Pitayevsky, you can produce the trefoil knot. And this is the difficulty that evidently everybody faces. To reproduce this precise geometry is the only way to produce a trefoil knot or any other complex, topologically complex structure. And with this precise geometry, you want to break the symmetry as well. Breaking the symmetry means that you can allow one reconnection to occur at a time. And this is exactly the way you can produce your complex. It's important for dynamical purposes to quantify certain things that for you are trivial, i.e. in this particular case, total length and total curvature of the system. Why is important? Well, is important because we have different rate changes here of total curvature and total length, and this gives us information of the approach and also information of the separation. Remember that these dots are closer to these peaks, and these identify the reconnection stage. In particular here, I have the 2-9 evolution, but of course we have these diagrams for all the knots up to 2-9. So all the sequence, the trefoil knot, the 2-8, the 2-7, the 2-5, etc. All the torus knots I showed you in the sequence. A further confirmation of helicity is obvious at this stage because the work is 22. So we just confirmed that Rife jumps through when we go this reconnection, and is compensated by the rise of a total twist. Okay, let me go on something else. Energy. Well, energy, of course, is very important for lots of reasons. If we consider Gross-Pitaevsky, this total energy associated with the system is given by this expression. I like to use a Madelung transform so I can interpret this expression in terms that are to some extent more clear to me. And by using Madelung transform, we can recognize this first term from this part as the kinetic energy. You see, it's a standard kinetic energy of classical physics, a velocity squared times density. Then we have a contribution in terms of gradients of this density, and this is called a quantum contribution to energy. Then we have a potential energy and interaction energy. And please note, these two contributions are expressed purely in terms of density rho. We want to say something about possibly Zyfer surfaces or isophase surfaces of a particular type, of a minimal area. Let's see if there is anything sensible to say about these surfaces, because, as I told you, this has a fascination for me in thinking of the soap film problem. Minimal area means simply a minimal area of our surface, S. And this is a bit tricky here, because we have to consider, well, first of all, these are constant, and so we can neglect these in terms of the energy. But then we can do a close-up view of these surfaces, and this has been done very meticulously by Simone Zucker, an amazing piece of work of computational research he did, because he screened all possible isophase surfaces around the defects. So imagine to screen, of course, not infinitely many, but many isophase surfaces over the 0, 2 pi around the defect, and then looking for information on each of these defects. Well, you can, of course, do computationally aided research on this, and you can prove computationally that you can define a new surface, say an S prime min, on which rho is basically constant. Remember that there is a reason for this. The variation of density are highly localized on the defect line. We are talking really Armstrong. Away from the defect line, density goes to basically constant value. So when we consider the gradients of rho that matters, we are extremely close to the defect line, and the contribution to the surface as mean or as prime mean don't make much difference. So we can assume that our minimum surface, or actually the search for minimum surface, is done now on S prime. So we exclude the points where grad rho are different from 0. We assume that rho is a constant from now on, but now we have the benefit that if rho is constant and u is a grad theta, then divergence of u is 0. So we have a theta that obeys to the Laplace equation. And this is wonderful. We are back with harmonic functions and elliptic functions. So the S prime min is critical for the Dirichlet energy. Now, this Dirichlet energy is expressed in terms of this potential psi. Let's have a look what is this Dirichlet energy. Under this approximation, the Dirichlet energy comes up to be just the sum of these two quantities, and indeed is what we expected, the contribution from kinetic energy and the contribution from quantum energy. Now we are ready to explore how these quantities are on this particular surface as min. Now, if we do that and we run it on time, we can get several diagrams for all the topological types investigated. Here, I show you the 2-9 because it's the more complex knot. And for all the knots investigated, the minimum area diminishes almost, let's say, monotonically, or allow us, you have to allow these jumps and this change in the monotonicity just because it's the numerical evolution. And then there are these tracts, these parts that seem to imply that there is a kind of change of concavity. But remember, when we are at this stage, we have effects of the numerical box back on the defects. So we presume are just due to numerical errors. Well, of course, these have been done several times, refining the grids, etc. Now, an amazing piece of work that Simone did is to confront, to check, and to look for the maximum of Dirichlet energy, screening all possible isophase surfaces, if you like, all possible Cypher surfaces of the defects, and confront this compare this with the Dirichlet energy calculated on the minimum area, and we see an exact superposition. So that means that indeed the minimal area Cypher surfaces are catching up the information, that they are good indicators that indeed the kinetic energy, if you like, is maximized, and the evolution is governed by a time increased sequence of information. Now, if we go for why I said that, sorry, I want to go back. There is a reason for that, well known to experts in the field. The Gross-Pitayevsky itself is time reversible, and so all information that we can provide in terms of irreversibility are useful. Now, the last part of my talk, I want to tell you something else. I want to investigate, due to the constraint, remember, of the fact that we have the sum of all linking numbers equal to 0, I want to investigate what happens if we try to unstabilize the system. In other words, if we can we try to change, twist or writhe of the system. So one easy example is this, or at least computationally easy example is this. Let's start with our vortex ring. There is no twist there, and we assume, of course, there is no writhe. It's totally isolated, no Gauss linking number. And you see this picture from Simone again of this isophase surface going around on these superposed on this vortex ring. Now, there is a hydrodynamic interpretation of this situation that I like to propose you, because it allows you to figure out what happens with a classical vortex ring. And the hydrodynamic version would be this. We have a vortex ring like this and an azimuthal flow around it. And so the vortex ring propagates along the axis, as we know from smoke rings and vortex rings in water. Now, suppose that we superimpose a twist, and we superimpose the twist so that the defect is still planar, so the writhe is still 0, but on the defect, the Cypher surface is slightly twisted. In this particular case, one full rotation. Now, there is nothing else. So one wonders, we are going to break the sum equal to 0 of all linking numbers. Now, in this case, we have only self-linking number. Actually, we have only twist, because writhe is also 0. So what happens to this system? Well, this system, the cartoon you see here is indeed a cartoon, because as we launch the simulation, instantly, immediately, a defect is generated at the center. And this note as secondary defect has an interpretation also in terms of fluid mechanics. We have an additional contribution from this velocity field, xi, and this is like an axial flow on the vortex ring, and indeed a central vortex is formed to compensate these additional contributions in terms of velocity fields. Now, in terms of defects, this is an extremely interesting case. So I studied this case with analysis, and this was done in collaboration with my former PhD student, Matteo Foresti, and we took the modified, we took the standard Gross-Pitayevsky equation, and we modified the background wave function, including the twist effect through this factor. We ended up with a new modified Gross-Pitayevsky equation, which is given here. And this equation is again a nonlinear Schrödinger equation type, so nothing new, but there is another term here in terms of I, complex number, and this additional term makes things very interesting. Indeed, we can prove on the basis of this equation that the Hamiltonian that governs the defect of with a superimposed twist is non-emission. It means that it can gain or lose energy. Now we kept going, and we derived an instability criterion. And if there is no twist diffusion, in other words, if we inject twist locally, it stays localized. Okay, we have these results. But more interesting is that if we inject twist and we admit twist diffusion, this is the last case, we have a linear instability. And this is extremely interesting. So we went back to computers, and this is what I want to show you. So first of all, this allows us to introduce a new definition of twist. And this is really kind of new virgin territory. We introduce a definition of a global phase twist as is meant to be for most of the people. A phase twist is said to be uniform if we superimpose a twist that is present everywhere in space. And in other words, this U due to the twist is transported parallelly on each isophase surface. What happens then? Here would be a third movie to show you. Well, first of all, we have the rotation present everywhere under the condition that the total sum of linking numbers is 0. And so it means that suppose that a defect as a straight line goes or normally through the screen, you see the point there, then you have twist everywhere. If we have twist everywhere and we superimpose a twist everywhere on single defects, then evidently we have to satisfy helicity equal to 0. So instantly we have an additional production of a straight defect. Evidently you understand the linking numbers change, and they are changed in order to satisfy sum equals 0 of all linking numbers. Eventually we have a reconnection, and we can go on with our simulation just for fun to see that this gets perturbed as the new defects get reconnected and perturbed. But I promised there is maybe a new definition we can give, and this brings me to the end of my talk. And the definition is the following. This is the first picture of the movie I hope to show you. And the second definition is the following. What about having, I'm sorry to play with words here, a localized phase twist? I'm playing with words because twist is a global quantity, but I mean it to have it localized on the defect. A phase twist is said to be localized on the defect if it is confined to the tubular neighborhood of the defect. And here is my idea. Well, suppose we have a diffusion of this, and suppose twist is different from 0, and I start with ρ equals 0. Can we conceive something like this? And my answer is, why not? Okay, so here we have the defect. And as you see, there is no apparent rotation. There is no twist. Again, imagine that the effect goes through your screen, so it's normal to the screen. But now let's zoom in and imagine to go very local to the defect. We are going local. We still see the isophase surfaces going straight away, but very, very locally, we have a kind of spiral structure emerging. So we are in the situation where away from the defect, it appears no global twist, but we are on the defect, very close in the neighborhood of the defect, then we can see some localized twist. And this example is reminiscent of something that somehow all of us know. Well, if we play with elastic strings, of course, whatever twist we put on our elastic ribbon, it stays there because the material absorbed the twist and there is nothing else in the air. And so we can transfer this idea by analogy to our defects. We proposed to do this, and of course you would expect a conversion of twist to writhe exactly as it happens for elastic strings. Now here we are just in the realm of supposition. We did some analysis on this. We take a kind of test function for twist. You do just some computation on paper, and you can prove that if this twist stays localized on the neighborhood of the defect, then this is the situation.
This computer thing on.
Okay, so this is what I expect to get. And of course, this is entirely speculation, is based on a piece of theory that we published last year with Matteo. And with this, I just like to thank you for your attention. And my aim is still to show you the movies. So before showing you the movies, let me just display one slide where all the references are there. So anybody interested can take a look or take a note. Slides will be made available. And the last reference is exactly the work we did with Andrea Belloni on proving rigorously by distributional techniques that zero helicity condition is indeed satisfied for quantum defects. This has been puzzling people for a number of years, and so we are quite pleased about that. To the movies. So this is the simulation. You probably see also time here. I click on time, and as you see, the torus knot rotates as well as translating along the Z direction. And you see that at a certain point, more or less when I didn't keep track of time, but eventually I run it again. Probably now you have an instantaneous reconnection at all places, and expect a further reconnection instantaneously where you see the highly bent system, one here, one there. You see the strands get closer and closer, interact, and here we have the formation of the all loops. So this is what I call the cascade process. Of course, the loops disappear. Imagine, of course, they don't disappear physically. Imagine that these little loops escape from your box. So let me run it again, being close to the reconnection. So you see here, because of the symmetry of the system, you have instantaneous reconnection at all points, and the formation of this wiggled loop. And then as we proceed, the formation of these smaller loops. So this is a kind of crash cascade from whatever tune 9 knot down, straight down to the last step of my sequence, where there were several loops formed. And then, of course, okay. So here, remember, we have two unlinked loops, and they're pretty well visible on this movie. I run the movie, and I run it again, And you see the business here, remember, is to break the symmetry of the system. If we break the symmetry, then you might expect, indeed it happens, that reconnection takes place at one site only. And this is what we want. You see, if I stop here, you see very well a loop that goes around, highly convoluted, of course. And we keep going. There is a secondary reconnection here in a moment. And here you have it. And then you have this Hopf link formed. And then I run it again. And as we proceed with time, we have again a third reconnection stage, a loop forming, and then the trefoil. You see it here very well. I just froze the picture, just to the movie, just to show you. And then the evolution. This is highly distorted, so for some reason it doesn't rotate as it travels, but it should rotate if it were highly symmetric. Okay, and then the last movie, and nothing else happens here. Of course, if we would have more computational time, it would interact again, reconnect again, and do the cascade process that we expect, because this is a pretty generic aspect of vortex dynamics. Here we are. As I said, here, remember, we are injecting twist on one of the ring, and so you expect that something catastrophic is going to happen, because under GPE total sum of linking numbers is 0. So indeed, as I click on the arrow, you will immediately see the formation of a center defect. And here, oh, okay, this is a different case from the previous one. The previous in the slides was the formation of one defect line on a circle, because twist was superposed on a single loop. Here we superpose two twists, one on this loop, one on the other, and similarly we have the formation of this straight line. Now remember, what we see, as we don't see vortices in real nature, we don't see vortices in this simulation. These are just surfaces of iso density surfaces, just to pick up in terms of visualization the defect lines. And they get thicker simply because the density, the isophase, the iso density surface is evidently getting bigger. So let me run this again, and you see that very clearly. Of course, there will be a reconnection, etc., etc. So we can analyze the information in terms of how twist and writhe are distributed, etc. I confess that we didn't do this, because as usual, we are always looking for something new, and I expect that twist and writhe will balance each other, as I showed in the other cases. That's all, and thank you very much again for your attention.
Yes, thank you so much for this wonderful talk and exposition.
Oh,
Are there questions? I remember a movie you showed me from Alexienko, who produced on a long vortex line by reconnection a link around the vortex line.
That's right.
I have wondered over a few years, but not gotten in contact with him, whether he ever produced knots in his lines in a similar way. Do you happen to know?
You probably know well that I've been asking these to them, to the group of them, a number of times, and so I wouldn't dare to send an extra one email to find out. But as far as I know, I'm not aware of any progress on that. I'm sure they are working very hard, maybe my fault, to detect or to measure better a twist transfer through reconnection. It might be the reason why they didn't go for the knot. But as you can see, I can add one little comment here. I wrote a little paper many years ago now, maybe more than 10, exactly suggesting that the initial conditions to find the case that we produce with the GPE now. And this is the business. In other words, you have to prescribe a very precise geometry. Now, what computational work can do, as we know very well, is we can play with engineering, with the conditions, so that we can find out the right conditions, and then we can pass them on to real experiments.
Of course.
And this is my hope, indeed. Yes. Yeah. However, Lou,
and of course, different experimental setups have different geometries. Of course, like
yes,
has a turbine vortex, and so it's a different geometry than the
I can comment on that because I do have experience with interacting with many groups, experimentalists around the world, and I can tell you that it's extremely hard to produce these, and not only because we know it's difficult, etc., because, you know, if you do everything in water in the old style way, i.e. color the vortices and of course check on the reconnection details, etc., remember all the times you have to clean your water tank, clean, I mean clean, and redo the experiment. Plus, if you want to have a precise geometry as an initial condition, that means you have to engineer the orifices through which the vortices are produced in an extremely detailed way. You cannot do with graduate students. You have to engage several engineers, electronics, computing, etc. And this is no longer a cheap experimental setup. But one day, I'm sure people will find out a way to produce them. Yes. Not easy. Not easy.
Other questions? Okay, then we'll adjourn. Thank you again.
Thank you. Thank you very much.
And please send us.
Thank you, Renzo.
Please send.
Oh,
hi,
hello,
Sophia.
hello. Hi, Sophia. Thank you.
Please send me your slideshow and maybe a link to the movies as well, and I will make that all available in our Dropbox.
Thank you very much, and thank you everybody for having the patience to go through all this stuff. Thank you.
Wonderful, wonderful talk. Thank you very much.
Thank you all. Bye-bye.
Bye now.
Bye.